Alright, we're going to go ahead and talk about concavity right now. It's a property that a graph has. So just real quick in general, let me just draw something like this. This is an example of a graph that is concave up. And this graph happens to be concave up everywhere. And concave up, what it kind of means is upward facing. Okay? So again, this right here, this would be concave up. Over here would be an example of a graph that is concave down. And that just basically means downward facing. And we'll take a look in a second at examples that, a graph doesn't always have to be concave up or concave down. It can switch, but we'll deal with that in just a second here. But what I'd like to do is to try and figure out, gosh, how can we determine if we have a function whether or not a graph is concave up or concave down? And what I'd like to do is to start by looking at the slopes of this graph. Okay? So let's deal with the concave up graph first. So I notice on a concave up graph that if I look over here on the left-hand side, these slopes look very, very negative. Okay? I'm going to just assign just a slope to this just to kind of give us a feel for it. Let's say that's a slope right there. We'll call it m for the slope, and say equals negative 10. Say m equals negative 10 right there. And as I move to the left here, or as I move to the right, I'm sorry, I notice that now this slope right here is still negative, but it's not quite as steep. So that slope right there might be, negative, let's say 5. Okay? And as I go down here even further, the slope's even less steep. It's still negative, but not as steep, so let's say that slope's like negative 1. At the bottom right here, I notice the slope right here is definitely, flat at some point, so m equals 0. And as I move to the right of that, okay, the slope is positive, all right? So let's say that that slope maybe is m equals 1. And then as I move further to the right, the slope remains positive, yet is steeper. So maybe that's a slope of 5, and up here might be a slope of 10. So again, the idea that I'm seeing here is that I move from left to right on a graph that's concave up, the values of my slope increase. So from negative 10 to negative 5 to negative 1 and so forth. I'm starting at a negative 10 value and ending up at a positive 10 value here, and the slopes are increasing in value as I move from left to right. Okay? So the slopes are increasing in value. So, okay, that's what I'm going to take here. So a concave up graph, the slopes increase. Slopes increase. We'll just leave it at that. Okay, slopes increase. Now, we want to use calculus language. Okay, so slope is like a synonym for derivative. So, if I were to call, let me just name this graph. How about I name this graph F? Lovely name for a graph. Okay, so if this is the graph of f prime would be describing the slopes. So that means that on a concave up graph, calling it f, we're saying that f prime is increasing. Again, slope, f prime, they're synonyms. They're the same thing. Okay, f prime just tells us the slope of the graph. Now, let's think here. If f prime is increasing, okay, so that's kind of one way we can determine that a graph is concave up, and we will use that at times. But let's think about this here for a second. So I'm going to write something that I'll erase in a sec, but I said there's something that you have to remember, okay, in a prior video, and that is that f is increasing when f prime is greater than 0. Okay? And this right now is not connected to the concave down thing. I'm just trying to make a connection back to here, you'll see in a second. So I said f is increasing when f prime is greater than 0. So the idea is this, I used f here. Okay? I could have used anything. I could have said g, I could have used any type of function. And the idea is that whatever I use here, this is the derivative. F prime is the derivative of whatever this is here. Okay? So again, if I could have said g is increasing when g prime is greater than 0. Okay? So whatever I put here, the derivative would go here. So let's just say, for instance, I said f prime is increasing when, well, the derivative of f prime would be f double prime. So it's true that f prime is increasing when f double prime is greater than 0. Okay? So going back to this, if I have a concave up graph, I've just discovered that on a concave up graph, f prime is increasing, meaning the derivative is increasing. So therefore, I know that since f prime is increasing, I know that when f prime is increasing when f double prime is greater than 0. So on a concave up graph, f double prime is greater than 0. So that is an important thing to remember, because you have to remember when you're thinking concavity, for the most part you should be thinking, okay, concavity, second derivative, all right? If the second derivative of the function is positive, the graph is concave up. So that's a very important thing to remember and to keep in mind. So you'll see here, I'll just kind of go through quickly on the concave down, kind of the opposite is true. So in this case, the graph starts out as a positive slope, okay? So let's say that starts out at m equals 10, and I won't do as many, and I go up here, maybe it's now m equals, I don't know, 2. At the top, it's a slope is 0, so m equals 0. As I move to the right-hand side, now it's a negative slope, say m equals negative 2. And then I go down here, it continues to be negative, but it gets steeper, like m equals negative 10. So what I notice is that as I move from left to right on a graph that's concave down, the slopes decrease in value. Okay? So let's say I call this graph over here, well, I'll call this graph f as well. Why not? Just to maybe make it less confusing. Or maybe it'll make it more confusing. I don't know. But so on this graph of f here, I notice that as I move from left to right, the slopes decrease. And again, slope is just the derivative. So the derivative of f is f prime, so that means that f prime is decreasing from left to right. Okay? And just like, basically a second ago I said f prime is increasing when f double prime is greater than 0. Well, that means that f prime would be decreasing when f double prime is less than 0. Okay? So a concave down graph a graph is concave down when its second derivative is less than 0. So we definitely need to associate concavity with second derivative. And the sign of the second derivative determines whether the graph is concave up or concave down. Okay? Now, like I said a second ago, here's the graph that's always concave up, here's a graph that's always concave down. That's not always the case. There could be a graph that is concave up a portion of the time and concave down a portion of the time. For instance, let me just do something like this. Okay? So if I have this graph right here, if you look on the left-hand side of the graph, like if I cover this portion up right here, that's clearly concave up. It's upward facing. Now on the right-hand side of that graph, you can see that is downward facing. So the graph starts concave up, and then at some point, it switches to being concave down. And there's an important thing here. So again, this side over here is concave up. This side over here is concave down. Okay? And this right here, the place where it changes concavity, has a name. It's called a point of inflection. So a point of inflection is where a graph changes concavity. So that's definitely a vocabulary term you need to know. Point of inflection is where a graph changes concavity. And something we should think about, in order for a graph to change concavity from concave up to concave down, think about it here. A second ago we said, okay, if a graph is concave up, that means that the second derivative is positive. So the second derivative of this graph right here would be positive, all the way on this part where it's concave up. And then the second derivative of this graph would have to be negative on this portion over here. So in order for a graph to change concavity, the second derivative would have to change from being positive to negative, and therefore that would be where the point of inflection would be the place where f double prime is equal to 0. For the most part, okay? It'd be where f double prime is equal to 0, because again, to change from concave up to concave down, the second derivative would have to change from positive to negative. Okay? Now, there is cases where the graph can change concavity and not have a point of inflection. Let me just show you real quick here. So, something like this, for instance. Say I had a graph that looked like this. So there's a vertical asymptote at 0. On the left-hand side of 0, the graph's concave up. On the right-hand side of 0, the graph is concave down. Okay? So clearly there is a change of concavity that happens at x equals 0, but there's actually no point on the graph at x equals 0. So therefore, this graph would not have any point of inflection, even though there is a change of concavity. Now, in this case, where this graph is concave up on the left, the second derivative would be positive. Where the graph is concave down, the second derivative would be negative. So at x equals 0, there has to be a change. In this case, so the second derivative would be undefined in this case. So when you're looking for changes in concavity, we have to keep in mind that a function could change concavity when the second derivative is 0 or is undefined.